The quantum theory of matter details how wave-like nature of matter gives rise to its observable properties. Now, since this is a theory, formally the theory is developed based on some common assumptions or postulates, and there are 5 primary ones that we're going to talk about. I'm going to talk about the first one in this particular video. Now, I've written it up here. Basically, it concerns the wave function itself and how we interpret that wave function. So the state of a system, and that means, how we can describe a system, everything we can measure about a system, is specified by its wave function. So you can think of the wave function as being like this magic black box. And if we just know how to ask that box the right question, we can get an answer that tells us something about the system. Now, I want to spend a little bit of time not only talking about the wave function, but also reviewing some of the notation that we're going to be using commonly. Now, you'll notice that this wave function is written as a function of r and t. Now, the r is bold-faced, and typically a bold-faced character, and I sometimes will write it with a little squiggle underneath, is basically indicative of multiple coordinates. Right? It's a vector. It's a coordinate in 3-dimensional space. Now, it also, if this is a system that involves more than one particle, it could involve those three-dimensional coordinates for all of the particles. So it could have as many as 3n different coordinates associated with it. Now, what that means is that if we want a differential element for this system, we're going to have to include all 3 of those coordinates. And sometimes we'll write this just as a shorthand, especially if we're dealing with more than one particle, like this. I'll use a letter tau to indicate all of the possible coordinates that we might be integrating over. So what this means now is when we interpret this wave function, we often interpret it as a probability density, which means that when we talk about quantities like the wave function with its magnitude squared, if we multiply this now by a differential element, that this represents a probability density for finding the particle, which is one of the things that we might be interested in measuring for this system. Where is the system? Where is it at this particular moment? Now, we also know that waves are not specific in terms of where they locate things, but this would give us an idea of how probable it is for a particle to be located in a spot designated by this coordinate vector r. Now, what this also means, though, is that these wave functions must have the sum of their areas equal to 1, because ordinarily there's only a probability of 1 of finding the particle in the universe. So, for example, we might be able to write something that looks like this, where we're going to integrate over all of the x values and all of the y values and all of the z values. So when you see something like this, this is just saying we're going to sum things over the entire universe. And when we do this for this wave function, and I'm going to write it like this, this represents now our probability density that's written up here. And I've already got my differential element, so I don't need to include one over here. When I sum all these things up, they must equal to 1. Now, a shorthand way of writing this same thing is I might also just say from minus infinity to infinity, and we'll assume that this is over all the coordinates. If I take the square magnitude of my wave function, now integrated over all those coordinates, which I'm denoting by tau, that this would equal to 1. Okay, but you need to understand that when we use tau over here, we don't have just a single integral here. So at the minimum, if I have a particle, I'm going to have at least 3 integrals implied by this particular notation. I realize that this is maybe not as straightforward and as clear as you might like, but just remember, whenever you see the tau here, think of the number of variables as something that's going to be greater than what it looks like in that particular equation. So if tau is used there, it's probable that we've got more than one integral going on here. If there were only one coordinate, for example, we'd just put that coordinate there. It would be like dx. All right. So once we have a probability density like this, that implies or it imposes certain properties that we must have for this wave function. So let's talk about those for just a second. Okay, and what I mean by properties is really the mathematical behavior of this wave function, because we need to represent it somehow. And so I want to talk a little bit about what some of those necessary properties might be. Okay, first of all, this function, psi of r and t, must be continuous. In other words, we can't have a break in it somewhere. So if I were to draw this out, let's start to make a drawing here. And I'll just do this in one coordinate, although it could be in many coordinates, but hopefully the one coordinate will give you an idea of what this means. I can't have a wave function that's coming along and then all of a sudden there's a break and then it continues over here. Okay, this break here would never be found in a wave function that represents a physical system. Okay, another property that we necessarily need to have is that it must be continuously differentiable. What does that mean? Well, most of the time we think of functions as being very smooth, varying things. So in other words, if we were to take the derivative, we would be able to easily define the slope at every point along that curve. But what if this particular curve that I've drawn over here instead comes down to a point and then continues? Well, at that point, you can't define the derivative. All right, it's just not possible. It's a discontinuous derivative. So you would never find that in a physical wave function for a quantum mechanical system. Another thing that we must demand of our wave function is that it must be single valued. Okay, and I hope this one makes a little bit more sense perhaps, but in our drawing here, if I had a wave function that came up here and then it curved back here, it's no longer single valued at these points. It has two values at point x out here. All right, and we can't have a wave function that does that. All right, so all the wave functions must have a single value related to each value of x. All right, and no more than that. And then finally, and this really has much to do with the fact that we're interpreting this as a probability density, is that the area of this quantity, okay, when I take the square magnitude of this wave function, it must be finite. So I'll say must have a finite area. Now you might say, well, if it's adding up to 1, wouldn't the area have to be 1? Well, yes, it does. But we can artificially make that area 1 by scaling the wave function. In other words, just by multiplying it by a constant. And we'll see how that works. We've already seen how that works with the particle in a box. But we can normalize the wave function so that its area actually is exactly 1. But the first and more important prerequisite is that the function that represents that wave is something that has a finite area so that we have the opportunity to scale it and make sure that it actually can behave as a probability density. Now, these wave functions, I've drawn this specifically as a function of coordinate and time. Okay, coordinate r, time t. This is not the only way that we can represent wave functions. We can represent them in lots of different ways. Okay, so in this case, it's a function of r. It turns out we could also represent it as a function of momentum instead. So we have a choice between representing it as, say, psi of r or psi of p and t. Okay, we probably should choose one and not both. In fact, you can't do both. But the point is that there's many ways that we could specify this wave function, but they still represent the same state of the system. So one way to deal with this is to use a special kind of notation. Now, I will be using this special notation from time to time in the course, but I want you to understand how to interpret it as a function. Most of us are more familiar and comfortable with writing a wave function, as we have in all these places here. But there's a special kind of notation, and I'm going to give it a name. It's due to a famous physicist named Paul Dirac, who lived in the early, actually he lived to be quite an advanced age, lived into the 1980s, I believe. But Dirac notation would express this wave function in the following way. It would write a special kind of symbol around the wave function, which is called a bracket. This then is something that we would associate with this wave function psi of r and t. Okay, so this notation gives us a little bit simpler way to specify a wave function without necessarily having to give all the coordinates that it goes with it. Now there's another variation of this. We can draw this wave function like this. Okay, you see this sort of the backward bracket, but what this represents is the complex conjugate of our wave function. So you see he has a clever way of denoting the complex conjugate as well as the function itself. Now there's one other piece to this, and that is that we can combine these together, but when we do, it matters what order we put them in. So for example, if we put them in the order of this, then it implies that we're integrating over the product of the complex conjugate with the wave function. So one of these things that we've written up here, so for example, this particular statement could be written as this in Dirac notation. And I hope you can appreciate that this is a lot simpler thing to write than all of this stuff over here. And this means the same thing. So what I want you to get used to is understanding that sometimes when I write something like this is what I mean over here. All right, so that means I can write it a little bit faster and we can convey the same information in a much more compact manner, and that will make a lot of things easier, especially later in the course when we deal with wave functions that don't necessarily have an easy way to write them as a coordinate function. All right, so that's enough for postulate 1. We'll move on to some of the other postulates now.